Okay, thanks Nabila and Henry. Okay, this morning, we're going to do several things. Number one, peptide bonds. Number two, we're going to look at something called tertiary structure. Okay, first and foremost, let's look at peptide bonds this morning. I believe you learned about peptide bonds in JH2. Yeah? Okay, so I'm not going to spend too much time, but I'd like to spend some time to recap. Okay, Nabila has drawn two amino acids on the whiteboard. She has chosen to draw the ion form of them. Okay, so if you want to draw the ion form, make sure you include the charges. For example, if you see COO, okay, there should be a minus over here. H3, there should be a plus over here. Okay, same here. Here, this should be a 3, then there should be a plus, and then there should be a minus. Okay? However, I would like to advise that when you draw your amino acids, if we were to ask you to draw, can you draw it in the non-ionic version? Okay, that is the form that they actually react in. Okay, this ion form is not the form they react in. So, instead, if you draw it as NH2, COOH, NH2, COOH. Okay? Draw in a non-ion form. Next, let's look at the bond that has been formed. Okay, so assuming if it is NH2, let me complete the ends. Okay, what's good is that wow, my voice just broke there. Forgot to do my vocal warm up. Okay. So to form a peptide bond, what you need, right, is to water will come out. Right? We call that a condensation reaction. Okay, so water comes out. Very good. Here we see a peptide bond. Okay. I'd like you to draw a little bit more details when you draw a peptide bond. So what should it look like if you want to add a little bit more details? Your oxygen, I'd like you to show the double bond to carbon. Next, your hydrogen and nitrogen, I'd like you to separate it out such that the hydrogen is bonded to the nitrogen. Okay? So carbon, double bond oxygen, carbon also bond to nitrogen, nitrogen bond to hydrogen. Yeah? So that's what a clear peptide bond looks like. Okay, so over here, let me include that H. Okay, so this is what peptide bond is. What's good is that Nabila also drew water molecule. Okay, that is a full condensation reaction. You know the video has started?
Yes.
Okay, thank you. Let's look at the left. Here, we also see two amino acids bonded together. We see a peptide bond. Okay, very good. You show the double bond to the O, show a single bond to the hydrogen. Is this part over here hydrophobic or hydrophilic? We practice, we keep practicing our skill. Look at the bond. Look at this covalent bond over here. Look at the two atoms. Look at this covalent bond here. Look at the two atoms. Is this part over here likely to become hydrophilic or hydrophobic? Okay, so if you say hydrophilic, then let's go one step backwards. Why do you say it's likely to be hydrophilic? Let's use the vocab. What property about this bond, this covalent bond, makes it hydrophilic? Sorry? Okay, I'm here polar, right? Okay, this bond over here is polar. How you know? You see oxygen is highly electronegative. You want 2 electrons to itself, making carbon electropositive. Nitrogen here is very electronegative. You want the 2 electrons to itself, it will be electropositive. Okay, it's polar. So if I want to throw water molecules to it, the oxygen will be attracted to the carbon. Over here, okay, maybe over here, the oxygen will be attracted to the hydrogen. Okay? Yeah, I do my best to keep showing you as many polar bonds. Then you get more and more used to it. Okay? Okay, take some time to touch up your notes if you have not drawn in a peptide bond. If you are done, then let's do the reverse. Let's perform hydrolysis. Okay, I'd like you to go to 5.A, 1.5A, scroll to number 5. Observe this pentapeptide. I'd like you to put a cross where you think hydrolysis can take place. I'd like you to put a cross where you think hydrolysis can take place. How many crosses will you include? Can you try that now? You don't need to do alone, you can work with a partner. Where will you draw your crosses? At the same time, maybe you practice, can you highlight all the peptide bonds? I'm just going to ask how many peptide bonds we have here. Okay? Okay, so number 1, can you highlight the peptide bond? Okay, first practice. Number 2, can you put an X at where exactly you would hydrolyze it? Number 3, can you highlight in another color the R group of each amino acid? Okay, keep practice. Highlight the R group of each amino acid. Number 4, can you tell me whether this R group is polar or hydrophilic or non-polar? Hydrophobic. Okay, practice, yeah? Let's practice. Okay. So, how many peptide bonds do you observe? How many? 4, huh? Okay. 4 peptide bonds. Where will you draw your X's? Okay, this way you draw your X, huh? You draw it between the C and the N. Okay, that's where the bond breaks. Okay? Finally, where are the R groups? This is one R group. This one over here is a bit weird, right? It's like no R group. That's the special amino acid that we talked about yesterday. Glycine does not have an R group. This is a bit special. Next amino acid, this is the R group. Next one, this is the R group. This amino acid here, the R group, is it hydrophobic or hydrophilic? Yeah, I think if you check classification, we consider this a hydrophilic R group, a polar one. Okay. Let's look at this one. This one is considered non-polar, hydrophobic, lot of carbon and hydrogen. This one over here also non-polar, hydrophobic, lots of carbon and hydrogen. Yeah, so we keep practicing this skill. You must be able to make sense of the polarity of what we see. Okay, any questions? Yes. Okay, hold on. Yes, follow. Okay. Yeah. Okay, so there's a question. Here we have OH, and then we see quite a lot of CH2. Okay? I think there's another scenario where you saw NH2 and then there was a lot of CH2, CH also, right? But that one was classified under hydrophobic. Okay, my chemistry is not that good, but from my understanding, oxygen is more electronegative than nitrogen. Okay? What it means is that it really pulls a lot of electrons to itself. So it's actually a lot more electronegative than nitrogen. Therefore, it's a lot more polar than nitrogen. So its polar nature is stronger than that of nitrogen. Okay, so typically when you see O and an H, it's actually really, really polar. Okay, it's really polar. So, sorry, yes.
So if it's an NH2 that is a good one, it will still stay as
Say again.
let's say the OH is to NH2.
Then
Would it be hydrophobic? Because
I would think so. Yeah. Because of the large number of CH2 over there.
there are other.
But is there such an amino acid?
I'm not sure. Okay.
Sorry, say again.
I'm not sure.
You have a question?
No, I have the same question.
Okay. Yeah.
And what other properties like C that we don't know?
Say again.
What about like other properties of like acyclics or like polars?
Oh, okay. So typically you'll see a lot of polar groups, right? For example, if you see a C double bond to O, okay, that's polar. N bond to H, that's polar. O bond to H, that's polar. Okay? This one is the most polar. Okay, this is the most polar. So if you want to see this, you will take it that whatever thing you're looking at is hydrophilic. It's very polar. I would say if I have to put it on a scale, this one is the least. Then this should be the most. If I have to put it on a scale. Yes, Jeanette? Oh, yeah. Oh, in the exam, is it? Okay, so I'll never ask you to calculate out polarity, like how polar something is. That's why our very, very first lesson, I did get you to check the electronegativity to compare, right? But that was it. Once you... Oh, so your question is, if you were to see, and then how is people know which is more polar? Okay, so I just have to know, and we only have 3. Okay? Largely you only see these 3. In biology, in chemistry I cannot say. Chemistry has many, many different bonds. But in biology you see these 3 very, very often. And so if ever you see OH, take it that confirm it's going to be polar hydrophilic. Okay? If you were to see ions, let's say if you see COO minus, anytime you see a plus or minus, it's confirmed going to be hydrophilic. No other way around it. Okay? So take some time, touch up your notes. Okay, first part of today's lesson was purely about peptide bonds, how we form them, how we break them. As we go on today's lesson, we're going to do a hands-on activity. Okay, I will not be doing 6 onwards. 6 onwards is extra. Okay, 6 onwards is for fun. If you want to do, you can do. What is this? 8. Okay, as you touch up your notes, those that are ready, can I get you to download CA 1.5B? This is what we'll be using today to learn a little bit more. We're going to pass around some stuff in a while. Standard by CA 1.5B, I'm going to be passing around a pack of beads and squiggly stuff. So can I go catch? You all work together? Now start here. I feel like you are like very powerful.
That's it.
Do this like you want to. Okay, so CA 1.5B. Okay, have you got CA 1.5B ready? Okay, let's kickstart the lesson. Okay, first activity asks you to highlight the hydrophobic R group in yellow, hydrophilic R groups in green. Okay, you've done this just, right? You've just done this. We do it again, and this time round, by this time round, you color code it. Hydrophobic in yellow, hydrophilic in green. I'd like you to highlight the hydrophobic yellow, hydrophilic green. Okay, we're going to use different colors to represent different kinds of R groups today. Yes.
So the N and H are not considered as polar.
Oh, okay. Good question. When we talk about whether an amino acid is polar, non-polar, we don't consider all these fellas, all the peptide bonds. Okay? We don't consider the peptide bonds.
Really consider R group.
Yes, only consider the R group when we are characterizing amino acid. Okay? Thank you. Yes. Oh, okay. So, what to highlight for this, right? Okay. So, for this particular amino acid with only an H, can you highlight the H in yellow? Okay, it will behave in a hydrophobic way. You highlight the R group in yellow. So, am I right to say that you have green, yellow, So it's green, yellow, 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 correct? How many amino acids are there? There's 1, there's 2, there's 3, there's 4, there's 5 amino acids. You see? Okay, so it's green, then this H over here is yellow, this one is yellow, this is yellow, this is also yellow. So we have 4 hydrophobic R groups and 1 hydrophilic R group. Yeah? Now let's draw a cartoon version of this amino acid. Okay, everyone follow me. First amino acid, I'm going to draw it as a circle to represent the hydrophilic amino acid. Second amino acid onwards, I'm going to use squares and diamonds to represent hydrophobic R groups. Okay? Y stands for yellow, yeah? Then this one green. Okay, can you draw a simplified model of this amino acid now? Circle, diamond, diamond, square, rectangle, square. Okay, a simplified model of this amino acid first, and then I will do the next activity number 2. Yes. Okay, we draw a simplified model of the. We call this a polypeptide, yeah? Polypeptide. Okay, when we join many amino acids together, poly means many, peptide means peptide bond, many peptide bonds, polypeptide. Sorry, I put G or yellow for you to color it. Okay, you can color it green, color it yellow, 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 yellow. Okay, I don't have yellow or green markers. Okay, don't you draw this so nice, huh? Okay, so next activity. Can I get you to hypothesize and draw how this particular polypeptide will fold in water? We've done this before in lipids. Remember in lipids, I keep getting you to arrange the lipids in water, right? Okay, so for this particular activity, how do you think this string of amino acids will coil and fold itself in water? Okay, could everyone draw their best interpretation of how it will fold itself in water? Considering that these are hydrophobic, this is hydrophilic. How do you think it will fold? And then I'll invite someone up to draw how theirs folds. Perhaps I'll stop here. Use this simplified drawing to depict how the polypeptide folds. Okay? I need to give you all like 5 minutes. Okay, just 3 minutes up. particular exercise we're doing is just theory, so there's no right answer. In real biology, we do go in certain ways. What are you doing? Oh. Yeah? About 1 minute more. This is a very interesting class. I observed that some of you have made a real model using the wires as well as the beads. Fantastic. Yeah, make use of what you have. Okay, so I have a few interpretations now. I see real models, I see drawings. Polypeptide, how it forms. What? Why you look so shocked? Thank you. Okay, thanks, Ileana. Okay, let's look at Ileana's diagram. Here, she has clumped together all the hydrophobic parts and left out one hydrophilic part. Anyone has other drawings or interpretations of how this might happen? As I was walking around, I actually saw you clump together all the hydrophobic parts. Yeah? We kind of apply what we've learned in our first few chapters. Hydrophobic things in water will want to clump together. Yeah? They want to exclude themselves, like the hydrophobic sand we've been playing with. Okay? So the only thing that Ileana left sticking out is the hydrophilic part. Yeah, the one that wants to interact with water. That's great. I saw some physical models. Although, can you show your physical model up into the air?
How do you break it up?
How you book it up? Okay, never mind.
It's similar to
You Kai. Please, yes. What? Okay. Kai, could you show us your physical model?
It's like a snail.
Okay, she's not a snail. She's kind of rolled up all the hydrophobic parts. Where's your hydrophilic part?
It's red.
Oh, it's red. Okay. So she's used red to represent the hydrophilic part. Okay. Sorry, I'll hold yours up. Okay, we look at this model over here. Okay. Very fascinating. It's the first class I've ever been to all these years, right? That will immediately just use the beads. Okay. Okay, fantastic. So, what we've learned here is this, that how a polypeptide folds depends on what medium is put in. Right? Notice if we put it in water, it will fold this way. If we don't put it in water, chances are it won't fold. Okay? Yeah? Okay, so what we've learned so far at the very beginning, we learned that amino acids through peptide bonds, you will form polypeptides. What makes a polypeptide a protein? It's just one additional step. It's called folding. The polypeptide needs to fold to form a protein. What you've just done here is to form a protein from a polypeptide. Originally, a polypeptide is just a string of amino acid like beads on a string. Yeah. Okay. But we fold it. What we get here is a protein. A protein is just a folded polypeptide. Yes, Henry?
So if it's all hydrophilic,
Oh, okay. Great question. So Henry asked, right? If it's all hydrophilic, would there be a problem? Technically, if I were to dunk it in water, it just remain a thread, right? Yeah. Then technically it won't fall, right? So how? In reality, proteins, you will not find a protein with just hydrophilic or just hydrophobic. You will always find polypeptides with a mixture. That's why they always fold. Okay? You always find a mixture of hydrophobic, hydrophilic. Never will you find just one plane. Okay? Just to elaborate a little bit more, now I'm going to bring in levels of structure of proteins. Proteins have several structures, several levels of structures. The very first level of structure we call the primary structure. This over here is what I will call a primary structure. Let me define a primary structure a little bit more. Primary structure refers to the number, type, and sequence of amino acids. Okay, say again. The primary structure refers to the number, type, and sequence of amino acids in a polypeptide. And we can have many primary structures. For example, look at these 5 amino acids on a whiteboard. I'm going to show you 2 more primary structures using the same amino acids. Okay, number 1, let me change the number of amino acids. 1, 2, 3, 4. This is a different primary structure already. Let me change perhaps the type. 1, 2, part, 4, 5. I've changed the primary structure yet in another way. Let me change it one more time. Let me change the sequence compared to this one. Let's instead do diamond, circle, diamond, square, square. I've created 4 primary structures. The reason why it's still referred to as a structure is because notice that there is, in a sense, a structure, a different shape. Each amino acid has R groups that sticking out more, some sticking out less. In a sense, it's not just a straight line of a string. There's a structure along this line. Okay? There's a structure along this line. If I were to draw the amino acid out, just a silhouette of it, it will look like that. See, this amino acid bumps up like that, then there's a sharp bump, and then a square bump over here. So there is a structure. Okay, this is me drawing a silhouette of this polypeptide. There is a structure. Okay? So to sum up, primary structure refers to the number, type, and sequence of amino acids in a polypeptide. Yes, Jermaine.
Where do we find proteins?
Where do we what?
Like in our body, like where do we find proteins?
Where do we find proteins? Great question. Oh, it's everywhere. Okay, I'm going to tell you examples of proteins. Here are some examples of proteins you can find in your body. Proteins can be your hormones. You know what hormones are? Hormones are made out of proteins, some of them. You know what enzymes are? Enzymes are also made out of proteins. You know your hair is made out of proteins also. Your nails made out of proteins too. Proteins can give structure. It can carry out chemical reactions. It can make your body grow like hormones. Okay, so proteins serve a lot of different functions. Yes?
Does the protein in our hair fold like the polypeptide?
Does the protein what?
In our hair, like do they fold like the polypeptide?
Oh yeah, so remember definition of protein is that it's a folded polypeptide. So your hair is straight. But if I were to zoom all the way, you will find that it's made of proteins that are folded.
But don't they only fold in water?
Oh, okay. Don't they only flow in water? Okay, that's a good point, huh? Don't they only flow in water? We will see in a while that depending on what R groups are present, some of the R groups present can help to form bonds between each other. Okay? Remember, technically if we have two hydrophilic things, they can hydrogen bond to each other. Yeah? So actually proteins can hold themselves to each other without water also. Okay, simple, eh? Okay, so earlier on we saw that all these polypeptides can fold. Right? And Liana drew a folded polypeptide. So she drew it like that. Huh? Yeah, I drew it very nasty way. And then there's one sticking out. Okay? Now this is a protein. Huh? What do we refer to this polypeptide? We refer to this structure as a tertiary structure. Okay? A tertiary structure is a structure where the polypeptide is folded in a very large scale. So let me list down some properties of a tertiary structure. Okay? Number one, there is large scale folding. Number two, it often ends up forming a 3D, what we call a globular shape. Okay, a globule is like a lump. Okay, a globule is like a lump. So very often, polypeptides will fold to form a 3D globular shape. Which is what is formed over here. So this is just a lump of polypeptides folded. Okay, so for today, we learned two levels of structure. First level is the primary structure, which refers to number, type, and sequence. The next level of structure is tertiary structure. I've jumped several steps up. Tertiary structure, which is large scale folding, which is what you've just done. We'll look at the thing between secondary structure and other day. Okay, if you are done, I'd like you to empty out the beads from your Ziploc bag. We're going to do an activity. I'd like you to scroll down to 3. Okay, right now, I would like every group to choose one primary structure to work with today. Can you decide among your group which primary structure you want to play with today? 1, 2, 3, or 4? Next, once you have chosen your primary structure, this is what you do. Notice that I provided a series of alphabets. Yeah? These alphabets represent amino acids. How you tell what's what? You go to your notes. So you have to work together as a team. Huh? One person should access the notes, one person with the worksheet. Okay, if you go to your notes, open it up, zoom in. Can you see that each amino acid actually has a code? R stands for arginine, H stands for histidine, K for lysine, so on and so forth. Okay? Last but not least, remember I told you yesterday the special cases, you can lump them as hydrophobic amino acids. So what's the task for this morning? The task for this morning is this. We are going to, number one, create a primary structure in real life. So what you will do as a team is this. You will first, number one, color code all your amino acids. Using green to represent hydrophilic R group, yellow hydrophobic, red to represent acidic R group, blue to represent a basic R group. First step I'd like you to do is use your highlighter function or color function. After you've chosen a primary structure, I'd like you to color each amino acid to the correct color. Once you are done, then you can start using the beads to string together your primary structure in real life. Okay? Could I get all of you to work on your primary structure now? You have 10 minutes to build your primary structure. Acidic or basic, please raise your hand up. Okay, you have your list.
So up here, all of the ones are oh, actually you see, like aspartic acid, bases are the ones on the left side. All the bases. A negative charge. The bases will have a positive charge. Oh, they are still acidic or basic, it's just that you not gain or lost activity. So typically in a question, I will show you if it's us. So because it's hard to whether it's acidic or not, just not.
Yeah, you must work together to accomplish this task fast. Yeah. Around 5 minutes more. I'm going to extend the time a bit more for you to build it in real life. Yeah. Around 5 more minutes to build it in real life, your primary structure. Yeah. Oh, red or yellow? They just leave a blank pen then. Okay, if you run out of beads for that color, you leave a blank.
acidic R groups are all the ones over here with the name aspartic acid. Okay, and also you know the CO minus. So anything with that is acid. Anything that has a positive charge is considered positive. So alphabets are this here. Leave it blank.
Done, you're supposed to take a photo of your primary structure and insert the photo in the space provided. Okay, I still see some of you still building. Okay, maximum, I'll give 2 more minutes, last 2 minutes. For those that are done, can I get you to insert a photo? For the rest, you have 2 more minutes to complete the task. done, I'd like you to read the next section. Stand by for the next section. It's a highlight for today. Say again, if you're done, please read the next section. See what you
every time we fold
how about you close it up together? Yeah, Ayo, so nice. Oh. Okay, can I get all of you now? Okay, your polypeptides that you form, the primary structure, can I get you to hook the ends so that the beads don't fall out? Okay, can you bend the wire at the end? Can you bend the wire at the end so that it does not fall out? I say again, can you bend the wires at the end so that it does not fall out? Hey, what do you do? Oh, you take it out. Hey, don't take it out. You need to use it for the next activity. Okay, do not remove all the beads. Yeah. Okay, then you take out 2 beads at the end. Okay, 1 from each end. Okay, let's go into the next activity. Okay, activity 4. Next. Just now we did it in theory, right? Ileana came up to draw in theory what it looks like. Now let's do it in real life. Imagine now with your primary structure is submerged underwater. How do you think your primary structure will fold? I'd like you to spend the next 2 minutes to fold your polypeptide into a protein that has been submerged in water. Please do so now. Once done, I'd like you to take a photo and insert into your CA. Are you done folding? Once done folding, I'd like you to take a quick photo. Then we'll look at some of your models. Okay, the clue, you are submerged underwater. Oh, okay. Oh, this is the oil version. So what was the water one? This is water. Would you think it's the best configuration, considering that this is the... Okay, do it. Yeah. So your hydrophobic class are like exposed to water. Okay, I'm about to showcase some of your friends' work. Now, when I bring a lot of stuff to class, okay, I need to tell you, it takes a lot of time to pack all these things. Yeah? To cut all the things out, to pack them into packets, to distribute, collect them back. So when I ask for you to participate in activities, I expect participation. Yeah? Don't just sit there and do nothing. Okay? You're wasting your time, not mine. Yeah, I say again, you're wasting your time, not mine. At the end of the day, you're the one that shortchanged yourself. Okay, let's have a look at some of your work. Wow. Okay, let's look over here. Remember, they submerged their primary structure of the polypeptide in water. Will you share with us the thinking behind your work? Okay, so the hydrophobic parts will clump together, group together. Okay, and then the hydrophilic parts are kind of all on the outside. Why do you put the hydrophilic parts on the outside? Because it likes water, okay? Do you think this is a fair enough fold? Yeah, this fold kind of makes sense, right? Hydrophobic parts want to escape water. Then hydrophilic parts kind of wrap around. Okay, interesting formation. Okay, let's go around. Okay, this one over here is interesting. Rather than a flat pretzel, okay, it kind of goes into a ball. Yours also not really like a flat pretzel. It's kind of like a ball. Will you share with us your interpretation? Why is it this ball shape? Why is it this globular shape? Why is it this globular shape?
The hydrophilic part likes water, so you will let the hydrophobic part hide inside.
Okay, so cute. Okay, so the hydrophobic part like water, right? So you will tuck and hide the hydrophobic parts inside. Actually, what alpha and powder has just formed is a globular shape. A globular shape is a shape that is kind of like a globule. Not really a fixed shape, but it's kind of clumpy. Okay, that's the best way I can describe it. A globular shape. Okay, any others? Let's have a look. Wow, what about this one? Okay, still thinking. Okay, may I have a look at yours? Okay, let's look at this one over here. Kind of like Phineas group. It's kind of like a flat pretzel. Like from one perspective it looks like that, but another perspective is kind of flat. Okay? But the hydrophobic parts are kind of clustered in the middle. So it seems that there are two ways of looking at this activity. The first one is you're looking at it from a 2D perspective. Another one, you look at it from a 3D perspective. Understand that in biology, we are working with a 3D space. Yeah? So when you dip something in water, it actually works in a 3D space. You would form a globular shape. The 2D shapes you form, it's not wrong. In theory, that is right. But we picture biology in a 3D space. Here I have a simulation. If you were to go to Lumos, and you were to scroll all the way down, you will find a simulation of what you have just done. But you can play with it a little bit more. The green represents hydrophilic, yellow represents hydrophobic, and I've dipped it in water. I'm going to press play right now. Watch what happens. Kind of exactly what you just done. Hydrophobic parts clump together, hydrophilic parts kind of wrapping around. Except this is a 2D model, so we cannot quite see it in 3D space. Let's restart this again. Okay, let's change things up. Let me change. Get a new primary structure. Let's see what happens in water. A new primary structure. Again, it seems like the hydrophobic parts are coming together. Hydrophilic parts are away. What kind of interactions are taking place over here between the R groups? I think we've learned several interactions, right? So all the hydrophobic parts, what kind of interactions are taking place? Sorry? I heard it somewhere over here. Hydrogen bonds? Okay, so hydrogen bonds would be between hydrophilic things, right? So hydrophobic. If you have two hydrophobic things like a hydrophobic sand, what kind of interaction is there? Yeah, I mean the name hydrophobic interaction. Okay, so here you can expect to find a lot of hydrophobic interactions, keeping everything together. I'm going to write down all the interactions you can expect to find in a tertiary structure. Number one, you can expect to find hydrophobic interactions in a tertiary structure. Other things you can expect to find, you can expect to find hydrogen bonds. Hydrogen bonds will be, you see this green amino acid here and this green one over here, they are kind of attracted to each other. They are hydrophilic groups, they are attracted via hydrogen bonding. Okay. Henry, you had a question, right, earlier on. What if we have an amino acid that's totally hydrophilic? Okay, let's change it up. All hydrophilic. What do you think will happen in water? Yeah, we press play, see what happens. Yeah. Notice it doesn't quite clump together. But do you see them also sticking to each other in some areas? These interactions, you expect it to be hydrogen bonding, yeah? Hydrogen bonds. So they are clumping together for that reason. Let's change things up. What if it's totally hydrophobic? All hydrophobic. Okay, what do you think will happen? So you just like show me a quiz. Yeah? Yeah, I'd now like you to try this next. Oh, wait, you observe this? Do you see between cysteine and cysteine there's a yellow line over here? Okay. Actually, there's a particular amino acid that can form covalent bonds between each other. Can you go to your notes and look for cysteine? Cysteine comes with sulfur. If you look at the amino acid cysteine, where is it? Over here. Can you see it comes with a sulfur? Yeah? Okay, so this amino acid is special because if there are two cysteine R groups nearby, it can form a covalent bond. I'll show you what a covalent bond looks like. Imagine now there is one cysteine over here with a SH, another one by the side with another SH. What will happen is that a bond will form. Okay? Now we call that bond a covalent bond. Sometimes you will see it described as a disulfide linkage. Okay? Because there are two sulfurs. Yeah, I'm just listing out all the possible bonds you can expect to find in a tertiary structure. Yes?
Does it mean that it has a byproduct of hydrogen?
Oh, that means hydrogen will be released, right? Yeah, you can expect that to be the case. Yeah, so actually, this covalent bond to form, right, is a condensation reaction. Yeah? Only if you were to find two cysteines near each other, then this bond can form. Okay? Okay, so three kinds of interactions you can expect to find so far. One last interaction you can expect to find in a tertiary structure, ionic bonds. Okay, ionic bonds. This is the last interaction you can expect to find in a tertiary structure. Ionic bonds form between acidic and basic groups. You look at your primary structure now. Are there red and blue beads? Yeah? Actually, the red and blue beads will attract each other like strong magnets. Because the red ones, acidic, is COO minus. And then there's a NH3, which is positive. They will attract to each other via ionic bonding. Okay, so if it's a base, it's an acid, a base, the acid and base will be bonded to each other via ionic bond. So, with your primary structure, if you wanted to, actually you can rearrange the red and blue parts. You may want to bring the red and blue closer to each other. Because they want to be with each other to form ionic bonds. Okay, so 4 different kinds of interactions you can expect to find in a tertiary structure to hold that shape together. This shape is held together by all these things interacting with each other. If you're done, you can try the next activity. What would happen if instead I take your primary structure and submerge it in oil? How do you think things will change? Okay, can you try that now? What will it look like if you submerge it in oil? That's our last activity for today. Are you done? Is this the oil one? Maybe while you're at it, you want to bring the blue and red parts together to form ionic bonds. Now the yellow is on the outside. Not really, but the hydrophobic is kind of oily. Once done, snap a photo. Now I'll show you the simulation what to expect. Sorry class, do you know where to find the link for Lumos? Okay, if you don't know, you go to the class chat now, then you look under group description. I think I put it there. The link to this website. Yeah? Hey, who here has gone to the website before? You went to it once? Yeah, so if you must be wondering, right? Every day I record lesson for what? For myself, I go home and then I sit at my couch and then I'm like, oh yes. So exciting. No, not for me. Okay, it's for you. Where can you go to find all of lessons we have in class? Okay, no, sorry, can someone check the WhatsApp group? Have or not? Okay, group description. I'll show you. If you were to scroll to if you were to go to the main page of Lumos, you'll find a playlist of our lessons. Okay? It's updated one, it says updated as it can be. So you see, term 1 week 9 303, that's just yesterday's lesson. Okay? So if you sometimes your body is here but your mind is not here. So if that's the case, please go and rewatch the lesson. But anyway, why am I showing you this? Because this is where you can find a lot of resources. Other than lessons in class, you can find every topic we are going to learn in our 2 years together. Okay? So for example, let's go to biomolecules. Here you can even find me teaching each topic. Okay? So you don't feel like you cannot catch up. I've taught every topic here, you can just go and watch. That's just me teaching. I give you an example. So you see carbohydrates. Okay? Then I teach step by step. Yeah? Okay, so if you scroll down, that's where you can find the simulation I was playing with. I would like to show you the simulation now. Look, I can add in now the acidic and basic groups. Just nice in colors, blue and red. Okay, you see acidic and basic groups. Let's watch what happens when I put in water. Notice the acidic and basic groups will want to be, they're not very close to each other. As close as it can be. Yeah. You can see hydrophobic interactions. Okay, you can see some hydrophobic interactions between hydrophobic groups. You can see hydrophilic interactions, sorry, hydrogen bonds. You can observe covalent bonds. What we do not really observe is ionic bond. Let's try another primary structure. Restart, random mix. Okay, let's try again. Okay. Can you see one ionic bond now? Do you see any blue and red together? Yeah. So now we have an ionic bond up here. So you notice, depending on the primary structure, it can affect what kinds of bonds are going to be present. Yeah? The primary structure is a very powerful structure. It really changes how things will fall at the tertiary level. What if I put this in oil, which is what you just did? Let's change this to oil. Ready? So let's see what happens in oil. Yeah? All of the ionic groups and the hydrophilic groups clump together in the middle. The hydrophobic ones are now the ones on the outside. Yeah? Let's try another primary structure. Let's random mix. Okay? Look at where all the hydrophobic parts are. Now let's play. Notice the hydrophobic parts are now on the outside. Hydrophilic and ionic, the charged ones are on the inside again. So what's the lesson for this? How something folds depends on two things. Number one, it depends on the primary structure. Because the primary structure decides what kind of bonds can form or interactions. For example, whether a hydrophobic interaction forms, hydrogen bond forms, or covalent bond forms. Number two, it depends on the medium that the polypeptide is in, whether it's water, whether it's oil. Two things decide how a polypeptide will fall into a protein. Okay? The primary structure as well as the medium it is submerged in. Two things. Can you spend some time touching up your notes, including more things in your notes? Yes, Shami.
For this, are we assuming that the hydrophilic parts are trying to contain water inside?
Okay. Great question, Shami asked. Are we assuming that the hydrophilic parts are trying to contain a little bit of water inside? That's a good assumption. Because actually it needs water to be able to attract the middle, right? Yes. So we have to assume that there is a little bit of water here. That's why all of them are clumping and attracted to the middle. However, it's not wrong to say that they want to clump together because they are polar and they want to interact with each other after all. Okay, the groups are all polar, so they will attract. Kara, you have a question?
What if it's like pure oil, like no water?
Oh, if it's pure oil, is it? I would say if it's pure oil, it may just take a much longer time by chance that the polar groups end up bumping to each other. Okay? But if there's water, there may be a higher chance that the water will serve as like a nucleus to attract everything together. I just realized one additional function, vacuum. What do you think will happen in a vacuum? No oil, no water.
Let's stay like that.
Now, what do you think will happen? Vacuum. Okay, how long you think you'll stay like that? Sir? Straighten up. What do you think? Separate. Okay, I honestly don't know. It's my first time I noticed about vacuum function. You ready? Let's see what happens in vacuum. Okay, remember, two things decide how a protein or polypeptide will fold. One is the primary structure. Depending on what amino acids are present, they will decide what kind of bonds can form, right? Number two, the medium. So if we don't have any medium now, vacuum, technically we still have one more thing to help in folding. Let's see if that one thing plays its part. If it doesn't, right? Yeah, go on. Let's go, play. So can or not? And proteins can still fold. So this protein is folding and is depending solely on the amino acid R groups. But notice that the hydrophobic ones aren't clumped together in the middle or outside. Hydrophilic ones not clumped in the middle or outside. That means the medium only determines one thing. It determines whether the hydrophobic or hydrophilic things are going to be inside or outside. That's the main thing it really determines, right? Because now that we've removed this factor, we notice that they can still bond. I really like this simulation. If you want to play this simulation, please go to Lumos. You can play with it. You can screenshot also, and then you can put it to your notes. Okay, that's all for today. I don't want to overload you anymore. We will do the rest another day. We have another day together. So that will be next week, right? Next week we have 2 more lessons, and then you will go. Hey, after that, March holidays already.
Yeah.
What?
Cannot be moved up.
Okay, I will see you next week then. Then we will work on this over here. 2 more lessons. Okay, I think we have enough time, so I will not give you homework for this particular day. Okay, I take the rest. In the remaining time, can I get you to pack up the beads? Can you take out all the beads and put it back inside? Make sure you take out the beads from the wire so that the next class can work on it. Once done, pass the ziplock to the front. And once you're done, can I get you to work on your notes? Look at your textbook. If there's anything you want to include from the whiteboard, that's a good time to do it before we erase it. You have any tests this week? Tomorrow. Read that one. Yeah, then we go. Okay, the rest of your class, then we come back from March holidays, we have a quiz. Did I tell you you can make notes and use it? Okay, so let me tell you right now. When you come back from your March holidays, there will be a quiz. What will this quiz be on? All the biomolecules. Okay, so it includes chapter 1 on bonds, chapter 2 lipids, carbo, nucleic acids, proteins. Okay? Okay, but here's the catch. What is the point of doing quizzes? to make you stress. Okay, I don't want that lah. Okay, so I'm going to change things up a bit. Instead, I want you to use the quiz for a more meaningful purpose. What would that be? Is this March holidays, can you make notes for each chapter? Okay, but I want you to challenge yourself. You can only use one side of an A4 for each chapter. Is it possible? It's possible. Huh? The more you use, actually, the less you are digesting. It is really possible to put everything into one side. Just like draw smaller lah. Okay. So, how many sides of notes can you make? 1, 2, 3, 4, 5 sides only. Okay. But what's the next thing I would like you to do? You know what? No, I realized one thing. That actually, when you make your notes, you will study your notes for your exam, right? But have you ever put your notes to the test? Never, right? Okay, so that's what the purpose of the quiz. I hope it can be false. I'll let you bring your notes for the quiz. Okay? If you don't make, it means you cannot use it. If you make, you know what it means? You can put your notes to the test. You can actually test to see if it's useful or not. Make sense or not? Okay? But I also want you to challenge your brain a bit. I want you to grow some muscles in there. Okay? So, I only let you use it towards the tail end of the quiz. The first part of the quiz, the large part of it, I want you to try without your notes first. Exercise your brain. Okay? So actually what will your notes be used for? Be used for the parts where you realize, I just cannot remember. Okay? Cannot remember, okay, I skip first. Cannot remember, I skip first. Then in the last few minutes, whatever time I give you, I'll say, now you can take out your notes, then you take out your notes. Okay? Okay, so here's the catch. Usually every year, with the classes, I'll give around either 10 or 5 minutes, depending on how long the quiz is. If the quiz is a short quiz, it will be 5 minutes. If it's a very long quiz, it will be 10 minutes. Okay? But I still want you to exercise your brain. Then, after you are done, you know what we will do as a class? You will then touch up your notes. Look at your quiz. Where did I not do well in? What did I miss out? Immediately go and touch up your notes. Make it better. That way, you tried and tested your notes. Cannot be that you study something that's not going to help you. I've seen students that make notes, they bring to the session, their quiz turns out quite bad. You know what this means? If you study the same notes for your exam, it's not going to be useful. Okay? So let's use the quiz meaningfully. Use it to test your notes. Make good notes over the March holidays. Okay? I would like you to scan and submit your notes onto Google Classroom so that I can see what you've done. And if I spot anything weird that you've done, I also can let you know. Okay? Let's work together, okay? So every quiz that you're going to do, I'll let you bring notes. That means to say, by the end of year, you would have made notes for every chapter. And you have tested all of them before. Okay? But you must work with me. Okay? If not, we revert back to the old format of quizzes, which is you just go in and whack. Okay? Thank you.